Hey guys, welcome to Unit 8, Notes A, Part 1. Right now we're going to look at acid and base theories. The very first theory ever created about acids and bases would be the Arrhenius Theory. But it's really limited and pretty much outdated, so it's really not a focus in the IB level of notes because their definition isn't very helpful. But I have to mention that this is where it all started. The Arrhenius theory states that acids would donate a hydrogen ion and bases would donate, quote, a hydroxide ion. But that's not really all there is to it. So the definitions that we use today aren't really tied to this definition. This was just kind of our starting point. The very first real tangible theory that started helping us to understand the behavior of acids and bases was the Bronsted-Lowry Theory. According to these guys, in order to be an acid, you would have to donate a proton or hydrogen ion. And to be a base, you would have to accept that proton or hydrogen ion. And I hope you remember from honors that a hydrogen atom is literally a proton and an electron, no neutrons. And so then if you create the ion, you're down the electron, and so all that's left is the proton. So these are basically synonyms, a proton and a hydrogen ion. Whenever an acid and a base react, they form what we call conjugate acids or bases. I like to call them more, or think of them more as complementary acids and bases. So the acid will form a conjugate base and the base will form a conjugate acid. And that's basically a way of showing that the acid lost the hydrogen and became more basic, and the base gained a hydrogen and became more acidic. Next, we're going to look at a way to label the acid-base, conjugate acid, and conjugate base of an example reaction. But before I do, I kind of want to talk about acetic acid, because throughout all of the IB stuff, they like to write it organically, but it really doesn't make as much sense acidically. So I want to kind of make a parallel here. So going back to honors, you may recognize the acetate ion as being written as C2H3O2, and it used to have a -1 charge. And so if it would bond to a hydrogen ion, that would neutralize the -1 charge, and we would have acetic acid. These two formulas are the same exact thing. Writing it organically tells me I have this methyl in front of another carbon that has this carboxylic acid group. I can tell that very quickly from the way it's written out, and that's the way IB likes to write things. But it can make it a little hard to think about in terms of acids and bases. So if it helps, underneath it, you can always write it out like this, because we will talk about basically double replacement reactions later on, where we're talking about the hydrogen ion being acidified. It's this hydrogen that is donated, and that's why it's called a carboxylic acid as a proton donor. So these are the same thing, just kind of wanted to explain that because you're going to see it a lot in these notes. Now on to trying to identify acid versus base on the reactant side. That's usually where you should start. So we just called this acetic acid, of course, and talked about how the hydrogen is donated. You can see that on the product side, the acetate has lost that proton, and that the water has now gained that proton. So this H has transferred to the water. That would make the acetic acid the proton donor, and therefore the acid, and the water the proton acceptor, and therefore the base. Now if you compare the acid that was originally acetic acid, it became just the regular acetate ion, or C2H3O2 minus. See the different ways that's written? Just kind of showing us the structure again. But the point is that it's down a proton, making it more basic. So that's the conjugate base to the acid. Those things are connected. And then if we look at the water, it was H2O, and now it became H3O plus, or hydronium. It gained an H plus, making it the conjugate acid. So first start with your reactants. Figure out which one is the proton donor by kind of comparing the products back to the reactants. And then whichever one gave up the proton is the acid, whichever one received it is the base. and then you find your pair, and the acid becomes more basic, and the base becomes more acidic. Next, we're going to look at some examples of how to identify the conjugate acid or base for certain substances. And these types of questions tend to throw people off more than normal. When you're looking at a whole reaction, it kind of makes sense because you can compare reactant to product. But you should be able to also, just for a specific substance, determine what would happen if it were to gain or lose that hydrogen ion. So for this first set, we're going to identify conjugate bases. So we're going to make it more basic, meaning we are going to lose a hydrogen ion. So we're going to knock off a hydrogen. So for example, with A here, 3 becomes 2. We're also going to make it 1 less positive. So if it's plus 1, that would just become neutral. And so this would become H2O. For B, when we knock off the hydrogen, 3 becomes 2. And then if it's neutral and you knock off a positive, our NH2 would gain a minus charge. You're going to see something similar in the next one also. Losing a hydrogen brings H2 down to just H1. So we have HCO3, and it's neutral, so it becomes a minus 1. Now I want to identify conjugate acids, which means I'm now going to gain that hydrogen ion. So 1 more H, and making it 1 more step towards the positive. The H is always going to go in the front. So for NO2 minus, it'll be HNO2, adding in that H in the front. And then the minus would cancel out with the positive, and it would just be neutral. So this is just nitric acid, HNO2. For hydroxide, as we gain the H, I bring 1 H up to 2, and then the positive cancels out with the negative. So this actually becomes what we affectionately know as H2O. Then we can look at CO3 2-, our carbonate ion, and if we add the hydrogen, we have HCO3, and then the 2-, I negate one of the minus charges, but one stays. So this is actually our bicarbonate ion. It can be easy to think of acids and bases as a black and white categorization, especially once you get into the properties section of these notes. But there are some substances that can act as either one, depending on the certain conditions they're in. So one word I hope you recognize from honors is amphoteric. Water is a great example of this. Another terminology that you might hear, especially internationally as an IB class, is amphiproduct. So that's pronounced, that PHI is a phi, amphiproduct. So two pronunciations, two labels for the same thing. Basically what we're saying is it can be an acid or a base. It kind of has this double identity. So for it to act as an acid, it has to be the one releasing the hydrogen. So it would have to be reacting with a protonic acceptor. And then in order for it to be a base, it would need to be the one accepting. So it would have to be reacting with something that's a stronger acid. So an amphoteric substance tends to be a little more neutral in the sense of pH. And it's able to go either way depending on which thing it's reacting with. If it's reacting with a stronger base, it'll play the role of the acid. If it's reacting with a stronger acid, it'll play the role of the base. So as I mentioned, water is a perfect example, and you'll notice it is no coincidence that the pH of water is 7, right in the middle of acid and base. So it's able to go either way. We will revisit what we covered in honors about how the water, it would take 2 water molecules. One needs to dissociate to produce a hydrogen ion, which is very unstable and rebonds with a water molecule to form hydronium, and then we have hydroxide. So we call this the autoionization of water. It does have an ionic property. It will dissociate, and then you will have both water, hydronium, and hydroxide all in an equilibrium in pure, like, DI water. So we can take this water and we can react it with either an acid or a base, and it'll play a role to affect either the hydronium or hydroxide concentrations. So below we have a couple examples, one of each. So for water to act as a base, it's going to react with acetic acid. And we talked about the structure of this a minute ago. Remember, we're just losing that extra H on the hydroxide of the carboxylic acid group. And so that's gone now, and we formed hydronium. So that would make acetic acid the acid and water the base. Now let's talk about how ammonia becomes ammonium. In order for this to happen, we have to gain a hydrogen. So one of the water hydrogens is going over to the ammonia side. So now water is the proton donor, making it the acid, where the ammonia is becoming the acceptor, making it the base. Another very common amphoteric substance is bicarbonate. You might have noticed that we saw it as both a conjugate acid and a conjugate base of some very common substances. So in reaction A here, we have it reacting as an acid, where it's going to donate the hydrogen. So we have the hydrogen going over to the water to form hydronium, and then bicarbonate simplifies down to just regular carbonate. And then as a base, it's going to take in a hydrogen. So here we have the hydrogen coming from the water to the bicarbonate, so it's going to form carbonic acid, and then the water would be left as hydroxide. So add bicarbonate to your list of amphoteric substances that you should know. After Bronsted-Lowry created their theory, we had one more advanced, more comprehensive theory that we are also going to go over some new stuff about today, where the Lewis theory can help me identify an acid or a base based on what's going on with the electrons. And the new stuff is going to have to do with ligands and identifying which things have electrons in order to be a good Lewis base. So Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. In honors, we talked a little bit about how, if a substance gives up a proton, it can then accept electrons and vice versa. Kind of talked about the octet rule. We're going to look a little bit more about the mechanism of that today. So there's a specific thing that always happens in an acid-base reaction, also known as a neutralization reaction, by the way. And that is the idea that you will always form a dative or coordinate covalent bond. I bet if you look back in your honors notes, you'll see these words, but you probably didn't understand what they mean. But now that we've talked about dative or coordinate covalent bonds, you get it a little bit more. We have electrons that are on one substance, in this case substance X, and they're going to form a bond with some metal. And so then we will form what we know as a dative bond, where the electrons come purely from one substance. And so this is one good definition for neutralization. So let's look at the mechanism of how ammonia becomes ammonium. So originally we have NH3, which has the one lone pair here, and it's going to become NH4 without a lone pair. So that lone pair is going to bond with a hydrogen ion, and so this lone pair becomes the bond that holds it together. So we have learned that a dative bond is sourced by one thing, in this case the nitrogen, and we can actually draw that bond as an arrow to show that it is the coordinate bond. So the Lewis definition basically means that you have to have an electron pair to donate in order to be a Lewis base. And so we're going to look at some things that don't have traditional acidic markings, which was the main thing we used in honors, and we're going to have to find what would be the more likely electron pair donor and label that as the base. So this is the new labeling technique we need to get a hold of. One last little thing I want to mention is this little note on the bottom of what they're calling a curly arrow. Just basically don't draw a straight arrow, because that's what we use for reactants and products, right? Like the whole forward-reverse reaction thing. But basically, I was always taught to circle the electrons that move and then make some kind of curved arrow to show where they go. And this is going to be a really big deal when you get to organic chemistry, because half of organic chemistry is just studying the mechanisms of how the electrons move, where they're supposed to go in order to form the products. So showing that electron motion is traditionally done with these curved arrows. And hopefully you've picked up a few tips and tricks in terms of like color coding or using different kind of fonts and things to try to show and communicate what is going on. That communication you've learned from your lab reports can carry over into your tests on things like this. So let's look at another example. Here we have BF3, which we have evolved our understanding of its structure from having a resonance double bonded structure to an incomplete octet now. So we know that this has actually only 6 electrons around the boron and is totally capable of bonding with another. And so these extra electrons here coming from the ammonia are perfectly capable of nesting with the boron. And so we get a dative bond here between the nitrogen and the boron, where the nitrogen sourced those 2 electrons. And so the 2 kind of individual compounds can combine into one bigger molecule. So we have BF3 and NH3 combined all together in one big old molecule. For our last Lewis example, we're going to look at the formation of a complex ion. In this case, copper is the central metal ion and water is the ligand. I know this kind of looks a little bit weird. I don't really know why they didn't bother to draw the lone pairs and they're using X's. Just a weird IB thing, I guess. But you know the formation of water. We got 2 lone pairs on the water here. So those lone pairs, those electrons, are perfectly able to be donated to our copper ion. And so we have this formation of this complex ion. So it's typically, if you remember the formation of a ligand, the metal needs to be something that has empty orbitals in their D subshell. So there were certain elements that were good for that. So the main connection we need to make now is that ligands have lone pairs, right? That's what made them good ligands. Well, lone pairs make them good Lewis bases. So the connection here is that ligands are good Lewis bases. So we're going to try to identify good bases based on things that have lone pairs. So here are 3 of the most common good Lewis bases, or very good ligands. We have water, which has the 2 lone pairs on the oxygen. We have cyanide, which has a lone pair on both the carbon and the nitrogen. And then we have ammonia, which has the lone pair. And if you remember the trigonal pyramidal structure of ammonia, that lone pair is way pushed out at the top of the pyramid, so it's very ready to bond. So we have all these lone pairs that are ready to go, ready to bond. So here's a pretty good summary or visual of the differences between our main theories. Notice Arrhenius Theory is kind of not even in the picture anymore. It's Bronsted-Lowry and Lewis theory, where the proton donor can then accept an electron and the proton acceptor can then donate an electron. And of course that always works, but there are some cases where a specific proton's not even involved and you can just look at the electron donation, which is where the ligand thing really comes in. So in that case, the metal isn't necessarily the hydrogen, it's some other transition metal or something. So there's a little bit of an expansion of that definition. So this little circle at the bottom here kind of shows that if it's a Bronsted-Lowry acid, it also is a Lewis acid. I guess same applies to bases, but not every Lewis applies to the Bronsted-Lowry definition. So it's kind of a circular definition. And if we did include Arrhenius theory, it would be this tiny little nutshell in here that barely covers anything. So that's why they don't even bother to mention it really in IB. So this is the new stuff. Now we're going to look at how to identify a Lewis base when it's not a typical acid-base reaction that fits the Bronsted-Lowry definition. We don't have proton donation here. So what we're looking for is that a Lewis base would be an electron donor, aka a ligand, something that's really good at donating electrons. So for part A, how in the heck could zinc 2 plus with like deficit in electrons ever be an electron donor? The ammonia, which has that pyramidal structure with the lone pair on it, that's going to be your electron donor, and so that's going to be your base, making zinc the acid. You don't identify conjugate acids or bases here because you're just forming complex ions, but you need to be able to identify acid and base on the reactant side. For the next one, the chlorine is our ligand. You may recognize these elements or compounds from the ligand kind of activity series that we've looked at before. So the pure old chlorine is going to have those free electrons. Like picture the Lewis structure of chlorine with a minus charge. It's going to have all 8 electrons around it. Plenty of electrons to go around. So of course that is our ligand. So that makes it our, here we go, Lewis base. This ionic compound of BeCl2 then, that would have to be our acid. It doesn't have any free electrons, they're all bonded in this ionic electrostatic attraction. The next one might be a little tough because we have the magnesium 2+, which obviously doesn't have lone pairs. I guess actually that makes it a little easier, but we typically don't think of water as an acid or base. But if you think in terms of electron donor, water has 2 lone pairs on it. That makes it a really good electron donor. Really good ligand, really good base. And so then we have the acid for the magnesium. So basically you're trying to find the ligand, and that's your Lewis base. So let's play a game of find the ligand. Which of these things could not act as the ligand or could not be the Lewis base? We have chlorine, which has 8 electrons surrounding it. We have NCl3, which has electrons around all the chlorine, but mostly, I mean, those really aren't going to react, to be honest. Mostly what would react would be the lone pair at the top of the nitrogen. The central tetrahedral shape would be what they're going for there. And then we have the PCl3. Again, this would be the lone pair that we're really interested in. But there are others where we really don't have any options, like nothing to donate whatsoever, is in the CH4. All the electrons are trapped up in these single pairs. So what are we going to have available to donate? You don't donate bonded pairs. There's no lone pairs here. So the only thing that absolutely could never act as a ligand is the methane, the CH4. Alright guys, that does it for Unit 8, Notes A, Part 1. There is a Part 2 which focuses specifically on properties of acids and bases instead of theories.